Hello all, thank you for attending the talk. The overview of a contribution is we make two major contributions. First, we know that there are highly sophisticated solvers for TFT, how the performance varies with different instances of solution. Our solution in this article is to come up with a parallel ensemble of solvers to beat the performance of individual solvers on a variety of problems. The second contribution is we use the different forms of mixing GA and EAX. Um, so since MGAs have slower conversions on problems larger than 2000 cities, we use a new hybrid algorithm to solve some of the hot PSP instances that are as large as 85,900. A little bit of background on the problem statement. The performance in solver varies with different instances. Existing approaches to this problem is algorithm selection using machine learning techniques, also to use hybrid algorithms. Yeah, so let's see what happened. In 2017, Kirk et al., they introduced 3 machine learning techniques on 5 algorithms, and they find out that EAX with the restart version is the single best solver. They also suggest that a hybrid of LKH and EAX might hold a significant promise. However, their research is limited to 2003 problems. In the same year, Sanchez, Whitley, and Tinos, they built a hybrid of EAX with chained LK, GPX, and GPX different version. They find out that GPX, the final version, reaches the global optimized solution. So they perform the hybrid solver for problems ranging from 5,000 to 13,500. I know the hybrid solvers are better when compared to EAX. How the GPX operator that they use has to be restricted because of the negative effects on population diversity. In 2020, Varadarajan and Whitley come up with a hybrid of mixing genetic algorithm that uses the GPX crossover operator. It does not lose any diversity in the population, so it combats the negative effects of GPX. And it's in a hybrid solver with EAX. It's able to solve some of the hot PSP instances. However, they did it only on small size problems, and also they found out that the hybrid is slow for larger problems. You see a trace of the graph in GA-EAX, the hybrid of the two. You can see that in the initial stages, the MGA, the blue and the green, the hybrid MGA and EAX are passed. However, in between 150 and 300 generations, the EAX cuts the MGA traces, and finally, EAX converges past, followed by the hybrid and followed by the mixing genetic algorithm. This is the case with problems higher than 2000 cities. So what we do in the new proposed hybrid algorithm is we run MGA in the initial stages, followed by EAX in the later stages. So that's what we are going to do. We propose a new hybrid algorithm running MGA in the beginning and EAX at the end. However, since MGA is slow for larger problem sizes, we do an island model design, divide the population among different computers. It has to be noted that MGA has a specific way of mixing things in the population, more specifically in a hypercube topology. So to divide this amongst the islands and do the traditional MGA is a challenge because if you see for a population of size 16, P0 is recombined with P8. So if we divide this into 2 islands, it's impossible to migrate all the individuals from one island to the other. So to overcome this issue, we use the mixing theorem property of the mixing GA. So the mixing theorem states that at the end of an epoch, so an epoch, they call the log P generation as an epoch, and the mixing GA progresses in epochs. So at the end of an epoch, the first individual is guaranteed to have the best portions coming from from the whole population. This is because P0, if we consider P0, it is the product, it is the result of the recombination between P0 3' and P1 3' here. And the P0 is the best child that comes out of the recombination. P1 is the worst child. So of the crossover operation. P0 3' and P1 3' are in turn the best and the worst coming out of the recombination of these four individuals. So P0, 2 prime, P double 2 prime recombine to form P0, 3 prime, which is the best individual. Similarly, P0 double prime to P3 double prime are the best individuals coming out of these 8 individuals. These 8 individuals are the best child coming from the whole population. So we use this concept. Instead of migrating the whole individuals, we just migrate the first individual amongst the islands. So in the island model version, we use the hypercube topology, and we would do simply the migrate the best individuals. So if you see here, I've put P1 to P8. These are the islands. Each block represents a subpopulation, and the green and the red circles represents the best and the worst individual at the end of the local epoch. The epochs are labeled as E1 block, E2 block, E3 block. So in the hypercube topology, there are 3 local epochs and 3 communication happening here between the islands. This is because, as you know, with hypercube topology, it just takes log to the 8, which is 3 steps to achieve the mixing of the whole population. So the pattern is again hypercube topology. P1 and P5 exchange their best individuals, the second P1 and P3, and so the locality, the Hamming distance between the islands keep coming down as you follow the hypercube topology. So to have a comparison with a different topology, we chose ring topology. Ring neighbors just communicate with each other. So for a given number of islands, 8, it takes 8 local epochs and 8 communication steps to achieve the mixing of the population amongst the islands. Note that in the 2 migration policies, we don't lose any diversity in the population. We simply keep migrating the individuals. So none of the edges are lost in the population, which is the property of mixing genetic algorithm. However, we do come up with some replace strategy. So if you consider the hypercube topology again, and the best individuals in P1 and P5, instead of simply getting migrated, we perform a local crossover operation and replace the best and the worst individual with the result of this crossover operation. So the worst individual in the population is always replaced. So we do this again in the hypercube fashion as well as the ring fashion. So there are 4 different models we propose to the island model design, coming out of 2 different topology and 2 different replace and migrate policy. And to achieve one full mixing, the ring topology takes 8 generations, whereas the hypercube topology takes 3 generations. And so we call this set of generation as one batch of parallel MGA. One batch is the time or the number of generations it takes to complete one full mixing. So these are the 2 differences. Ring topology takes I epochs to complete one full mixing. I is the number of islands, and the hypercube takes a log to the I epochs to complete the one full mixing. So putting it together in a parallel framework, we do one batch, but we could also do 2 or 3 batches. For our experiments, we chose one batch of parallel mixing GA. And at the end of the parallelization, we gather all the individuals and do a sequential EAX. However, note that there are parallel EAX version is available, but for this work, we chose sequential EAX because the parallel is not publicly available. So the experimental lab consists of 15 TSP library problems and population size of 256. Number of islands is 8. So there are 32 individuals per island, and we do this on a supercomputer. The results show that the replace ring strategy is fast on 13 out of 14 instances. You can see from the trace that replace ring converges fast, and EAX sequential is slow. Also, from all the hybrid versions, you can see that it's faster in the initial stages, and as against the hybrid version introduced by Varadarajan and Whitley in 2020. We see the EAX trace cutting the hybrid versions only at the later stages. So we can see that having MGA in the initial stages is highly helpful um, and improves the convergence of the algorithm. However, in terms of success rate, if you see EAX still outperforms the remaining things, overall it is 80.2% of success rate. This is understandable because EAX uses specific diversity preservation techniques. So when it loses edges in the population, or it does so very carefully, whereas with the replaced versions here, all the replaced ring is passed, the success rate is low because it just blindly removes the worst individuals in the population. So although it's fast, the success rate is lower. But when you look at the individual instances, hybrid is outperforms EAX on 3 instances, smaller or medium-sized instances, whereas EAX outperforms the hybrid on 3 instances. Hybrid and the EAX achieve 100% success on 9 out of 15 instances. Okay. So we cannot say that one thing is a single best solver. Of course, EAX has a higher success rate, but when we see individual instances, it's not the case. So to combat this issue, we come up with the parallel ensemble. So if you see the fourth column here, the sequence these show the results of sequential EAX. It achieves 24 out of 30 success rate. But when we run on ensemble of EAX, that is, we run 4 EAX in parallel, the success rate increases to 26.13. And this one shows the success rate of the ensemble of the 4 hybrid models is somewhere in between the sequential EAX and the ensemble EAX. However, if you see the individual problems, the U2319 is 3/30, whereas for the ensemble 7, and also for oral 5934, the sequential is 11, whereas the ensemble gets 30. Here also we get 30 here. The PLA EX does not solve at all, whereas the ensemble solves it. And similarly for USA, we get 17/30. The ensemble gets up to 100%, nearly 100%, as the ensemble of the hybrid gets only to 17/30. So we also get a significant gain with the time here because of running mixing GA in parallel. But also know that we are running mixing GA only one batch in parallel, it's just few couple of generations. But however, this time we have is because we are losing some of the edges in the earlier stages. That is helping EAX to run things fast at the later stage. Yeah, these are the speed up with respective generations for higher problem sizes. The EAX is the hybrid is fast compared to EAX. The fastest is the replay string followed by ensemble, and the slowest are the migrate version. This trend is true for the time speed up also. The replace versions and ensemble are fast, and the migrate versions are slow. And so the take-home message is the parallel ensemble is cost-effective. It's unlike the algorithmic selection using machine learning techniques. Compared to that, it's very cost-effective. And also, the hybrid can solve some of the hard TSP instances, higher success rate, and we tested on higher problem sizes. So these are the take-home messages. And one of the future work we did ensemble with LKH. You can see LKH as a 20 out of 30 is lower success rate. EX is 24, whereas the ensemble of the 2 is able to get up to 29, which is close to 100% success rate. And this 25.93 is coming from our mixing GA hybrid ensemble 2593. It is higher than the individual LKH and EAX algorithm. Finally, the full ensemble consisting of the hybrid models LKH and EAX is higher than the ensemble of LKH and EAX. If you can see, it achieves 100% on all the instances, and also on USA 13509, it increases the success rate. And also the execution, we get benefits of parallelization, effects on the execution time. So, so future work is to explore more parallelism, variety of solvers, and also variety of problems. With that, I end my talk, and I'm open to questions. Please feel free to email us if you have any questions or clarification or anything of the sort. Thank you.